Quantum computing and artificial intelligence are two transformative technologies that, when combined, create quantum AI. This integration leverages the unique properties of quantum mechanics, such as superposition and entanglement, to enhance AI's capabilities to solve complex problems, optimize processes, and analyze massive datasets. Quantum computing operates on qubits, which can represent multiple states simultaneously, unlike classical bits that are binary, 0 or 1. This allows quantum computers to perform calculations at exponentially faster speeds, making them ideal for AI tasks such as machine learning, optimization, and data analysis. OPTEX Quantum AI is the version of OPTEX that produces algorithms that can be solved on quantum computers. It inherits all the AI features of OPTEX Optimization Expert System. We can affirm that OPTEX Quantum AI is the state-of-the-art of optimization. The reasons are: generative artificial intelligence to produce the codes of the algorithms without programmers, and access to the world's fastest algorithms. Quantum computing, unlike classical computing, is a relatively recent development. Its origins date back to the late 1970s, when it first appeared in science fiction. In 1981, Nobel laureate Richard Feynman was credited with pioneering the concept of the quantum computer. His rule of thumb was, if you can't explain it simply, you don't understand it enough. In 1985, David Deutsch formalized the concept of a quantum computer, marking an important milestone in the field of quantum computing. Theory of quantum mechanics: it is the law of the smallest things at the scale of atoms and electrons in subatomic particles that causes an atom to overlap and become a state of having a combination of 0 and 1, it keeps changing. Superposition is the fundamental principle of quantum computing. It allows more than one bit to take on a single state, makes the operation of quantum computers faster, there will be two states at once, and much more information can be stored at the same time. Qubits are represented by a superposition of several possible states. A qubit uses the superposition phenomena of quantum mechanics to achieve a linear combination of two states. A qubit can represent a 0, a 1, or any ratio of 0 and 1 in the superposition of both states, with a given probability of being a 0 and a given probability of being a 1. The amount of information that a qubit system can represent increases exponentially. The information that 500 qubits can easily represent would not be possible even with more than 2 to the classical 500 bits. A classical computer to find the prime factors of a 2048-bit number takes millions of years. With qubits, this calculation could be done in a few minutes. Interference is a key idea in quantum computing. It is to control the probability of a system of qubits collapsing in measurement states. It is a byproduct of superposition. It is what allows us to skew the measurement of a qubit towards a desired state, or a set of states. Entanglement is like two objects connected in one way or another, that by knowing one of them, we can have a clear idea of the other, without having to measure it. In quantum computing, the probability of one qubit state can be affected by the change in the probability of another qubit state. This phenomenon is called entanglement, which is created through quantum gates by performing specific operations on the qubits that result in inseparable states of qubits. Quantum entanglement occurs when two or more particles are correlated, so that the state of one qubit depends on the state of another qubit, regardless of the distance between them. If the state of one qubit changes in the entangled system, the states of all other qubits will be affected. Just as a binary bit is the basic unit of information in classical computing, a qubit, or quantum bit, is the basic unit of information in quantum computing. The image shows how two qubits are in non-entangled, left, or entangled, right, quantum states. Quantum noise has several manifestations in quantum systems, and can affect various aspects of quantum computing. Some common examples of quantum noise include measurement noise. The act of measurement can cause a quantum system to lose superposition and collapse into one of its states, introducing uncertainty into the result, due to the probabilistic nature of the measurement process. Decoherence. Interactions with the environment can cause quantum systems to lose quantum superposition, entanglement, and interference, affecting the performance of algorithms. Quantum noise poses a major challenge for quantum computer science. To address this challenge, researchers have been working on quantum error correction techniques, which are essential for preserving quantum states against the detrimental effects of measurement noise and decoherence. Quantum approximate optimization algorithm and variational quantum eigensolver. Quantum computing is conceived as one of the potential ways to efficiently solve difficult combinatorial problems and overcome the current bottleneck. In recent years, many quantum algorithms have emerged that have demonstrated their novelty and potential to solve NP-hard problems, such as QAOA and VQE. The quantum approximate optimization algorithm, QAOA, is a variational quantum algorithm that aims to solve combinatorial optimization problems that are classically intractable. The variational quantum eigensolver, VQE, method is a similar quantum approximation algorithm developed independently of QAOA. In essence, both algorithms aim to find a ground state of a Hamiltonian with a slightly different approach. Using a quantum solver, such as QAOA or VQE, we can solve a mathematical model to obtain the optimal values for the decision variables, while satisfying the constraints of the problem, optimizing the target function. Several researchers have tried to find variations that produce better performance for QAOA and/or VQE than there are many options for quantum optimization algorithms. Quantum approximate optimization algorithm and its variations. QAOA hybrid workflow schematic with p-levels. The researchers evaluate an array of QAOA variants, namely, QAOA, QAOA Plus, Falcon, Modified QAOA, Warm Start QAOA and Ma QAOA. Each of these variants was chosen to represent a different methodological approach to improving the QAOA's performance. They illustrate some of the broad spectrum of ways that researchers have found to enhance the QAOA, such as adding features, speeding up optimization, adapting the ansatz, and utilizing previously computed information for a warm start. Composite depth of the QAOA and its variance on different max-cut problems using simulators, namely the depth of the circuit times the number of iterations required. This measure provides an agnostic indication of the computational time required on the quantum device. For the optimization process, the researchers used the Kobila optimizer provided by the SciPy library to tune the variational parameters in the QAOA circuits, in line with the results. The optimizer iterated until convergence based on the specified tolerance level, 0.0002, or until 500 iterations, whichever came first. The maximum number of iterations only influenced Ma QAOA, which often reached the maximum cap of iterations and needed many thousands of iterations to achieve just a slightly higher approximation ratio. The same optimization settings were used across all variants to ensure a fair comparison. Except for Warm Start QAOA, which provides a specific initialization of the parameters. This comprehensive review provides an overview of the current state of QAOA, covering its performance analysis in various scenarios, its applicability across various instances of problems, and considerations of hardware-specific challenges such as fault susceptibility and noise resiliency. In addition, a comparative study of selected QAOA extensions and variants is conducted, while we explore perspectives and directions for the algorithm. The aim is to provide insight into key questions about the algorithm, such as whether it can outperform classical algorithms and under what circumstances it should be used. Quantum adiabatic optimization, QAO, which can be applied to any constraint satisfaction problem, CSP, where they are given a sequence of constraints applied to some input bits and asked to generate an allocation to the input bits, which maximizes the number of constraints satisfied. The basic idea behind the algorithm is physical and is based on a correspondence between CSPs and physical systems. QAO starts with a quantum state that is the uniform superposition on all possible solutions for CSP. This is the lowest energy state of a Hamiltonian that can be easily prepared. This Hamiltonian is gradually modified to give a new Hamiltonian whose energy state encodes the solution by maximizing the number of constraints satisfied. QAO ensures that if the process is carried out slowly enough, the system will remain in its ground state throughout the process. In particular, the final state gives an optimal solution to CSP. The key is slow enough. For some problems of n-bit cases, the time required for the solution could be exponential in n. Quantum-inspired Ising machines, QIM, are classical computer systems designed to solve complex combinatorial optimization problems by emulating the principles of quantum physics, such as the Ising model, Using existing silicon-based hardware instead of true quantum hardware, QIAM mimic quantum properties. QIAMs, also known as annealing, are designed for specialized tasks such as those found in financial trading or drug discovery, offering scalable, low-power, short-term solutions leveraging physics-based principles to find optimal low-energy states. The key concept comes from Ising's model, which describes magnetism and how individual spins in a system interact with their neighbors to reach a steady, low-energy state. Combinatorial optimization. By mapping problems to this Ising model, these machines aim to find the optimal solution, the lowest energy state, for complex problems that would be intractable by classical computers. Due to the parallelism caused by quantum superposition and the tunneling caused by quantum fluctuation, quantum computers have great advantages over classical computers, in precision and/or efficiency. But quantum computers required rigorous physical conditions, such as ultra-low temperatures in confined spaces, or possessed large volume, facing enormous limitations for practical applications. The diagram shows a practical problem in a QIAM. To solve a practical problem, the puzzle must be assigned to the natural physical phenomenon corresponding to the property of convergence. The solution to the puzzle is measured when the system stops converging under the external field and evolution. Ising's most famous algorithm assumes that it is a quantum annealing based on adiabatic quantum optimization. Compared with classical simulated annealing, quantum annealing is superior due to overlap and tunneling. Quantum annealing produced by companies such as D-Wave has been operational for commercial use. The diagram presents the architecture of an Ising machine. Quantum-inspired solvers on mixed integer linear programming. Mixed integer linear programming, MILP, plays a crucial role in artificial intelligence, biochemistry, finance, cryptography, etc. Despite being popular for decades, research on MILP solvers is still limited by the resource consumption caused by the complexity and failure of Moore's law. QIAM as a new computing paradigm, can be used to solve MILP by reducing them to Ising models. Therefore, it is necessary to understand the technical evolution of quantum-inspired solvers to break the bottleneck. The paper discusses the challenges and opportunities of miniaturized solvers in the future. Known as the first commercial MILP solver, Express was originally developed in 1986. Subsequently, Gurobi, Plex and other commercial solvers have mushroomed over the past 30 years. SIP, one of the fastest non-commercial solvers for MILP problems, was developed in Germany in 2001 and has inspired the design of several solvers in China. Some efforts in quantum computing have focused on difficult optimization problems. While some non-von Neumann computers, such as general quantum computers and QIAM, have shown quantum advantages in maximal cutoff problems, protein folding problems, etc. Ising model and reduced MILP problems. Many combinatorial optimization problems can be reduced to Ising problems. The Ising model is a general mathematical model in statistical physics, which was first used to explain the correlation between spin states in ferromagnetic material and macroscopic magnetic moment. It assumes that ferromagnetic matter consists of a collection of small magnetic needles, of which each is only allowed to be either +1 or -1. Adjacent magnetic needles interact with each other across the field, combined with stochastic magnetic somersaults caused by interference from ambient thermal noise. The purpose of the Ising problem is to minimize the Ising Hamiltonian. Miniaturized solvers. Ising machines have advantages and disadvantages for solving practical MILP problems. A skilled solver should be convenient for practical use, i.e., it is supposed to be miniaturized without a harsh environment. Therefore, the following topics are needed to study further. Scalability of annealers. Limitation of SIMs from materials, and the reduction of MILP problems. Based on mathematical programming, branch and bound, cutting planes, and column generation are used to solve MILP. In addition, decomposition algorithms such as Bender's and Dantzig-Wolff are effective at solving large problems. A modified implicit enumeration method worked in pure integer programming problems that could be reduced into binary integer linear programming, BILP. The BILP schema can be directly reduced to the Ising model. However, outside of BILP, other MILP problems cannot be directly integrated into the Ising machine, as Ising's model is not capable of handling continuous variables. Although it is operable to split or convert MILP problems into BIOP problems, more efforts must be made, and quantum superiority decreases. One potential direction is to reduce the MILP problem to the Xi model. The MILP problem can become finding the minimum value of the mixture of Xi Hamiltonian and Ising Hamiltonian. IBM Quantum Platform provides access to quantum computers, documentation, and learning resources in one place. IBM Quantum is building a large-scale, fault-tolerant quantum computer. In 2029, IBM will deliver a system that accurately runs 100 million gates on 200 logical qubits, unlocking the first viable path to realizing the full power of quantum computing. The first quantum advantage claims are emerging, but how will we know when it has arrived? Researchers from IBM and quantum startup Pascal explore this and other questions. Just recently, researchers at the startup Kipu Quantum claimed a runtime quantum advantage, where their quantum algorithm ran faster than specific-purpose classical solvers for dense, higher-order unconstrained binary (HUBO) optimization problems. They identified instances that were challenging for methods like PLEX and simulated annealing and found that running their BFDCQO quantum algorithm on ever-improving quantum hardware reported faster approximate solutions. The results are impressive. BFDCQO can consistently achieve comparable quality and the yielded solutions for the tested instances up to 80 times faster than PLEX, or up to 12 times faster than SA. They expect their runtimes to be soon orders of magnitude faster as hardware continues to advance. The tutorial demonstrates how to implement QO within the context of Qiskit patterns, IBM's open-source toolkit for quantum computing. You'll first solve the maximum cutoff problem for a small chart and then learn how to run it at utility scale. The max cut problem is an NP-hard optimization problem with several different applications in clustering, network science, and statistical physics. This tutorial considers a graph of nodes connected by edges and aims to break it down into separate graphs so that they are both as large as possible. In other words, the objective is to divide the nodes of a graph into two sets in such a way as to maximize the number of edges crossed by this cut. According to IBM, Qiskit is the software of choice for the advantage era because it offers the most comprehensive set of open-source tools to advance research across the stack. Experience at scale with the world's fastest transpiler, preparing workloads 63x faster than the next leading SDK. Qiskit is the world's most popular and performant software stack for quantum computing and algorithms research. Build, optimize, and execute quantum workloads at scale. Gurobi, a leading optimization software, does not currently offer quantum algorithms as part of its suite. Quantum optimization is still in its early stages, and the practical, real benefits of quantum computing are likely decades away. While quantum algorithms such as QO are being explored in research, they are not yet integrated into Gurobi's offerings. Gurobi focuses on classic optimization techniques, such as linear programming, LP, mixed integer programming, MIP, and quadratic programming, QP, which are highly efficient and widely used in today's industries. This tech talk doesn't take sides in the debate, nor will it make predictions about the quantum computing capabilities of the future. It attempts to present the technical details of quantum algorithms aimed at mathematical optimization professionals. It's easy to overlook the connections between classical mathematical optimization concepts and quantum computing. However, many mathematical optimization concepts can offer guidance for solving challenging problems in a quantum computing environment. Quantum algorithms for optimization fall into two categories: quantum annealing and logic gate algorithms. The first part of the webinar is quantum annealers. That focuses on quantum annealing, as the connections to classical optimization. The second part is logic gate quantum that considers the logic gate architecture and the underlying linear algebraic concepts, which are familiar optimization users. The paper, Quantum Computing for Production Planning, presents a case of a QO application. This research investigates the potential of quantum computing in production planning, and addresses the limitations of conventional computing approaches, which have been partially effective, trying to solve complex optimization problems, accurately predict demand, and manage supply chains efficiently. The capabilities of quantum computing offer promising solutions to overcome these obstacles and revolutionize production planning processes. The research methodology to explore the potential of quantum computing in production planning and address the stated research objectives will involve a combination of theoretical analysis and practical experimentation. The methodology can be summarized as follows. Literature review. Analysis of classical production planning methods. Understanding quantum computing principles. Formulation of the production planning problem. Development of quantum algorithms. Experimental evaluation, and analysis and interpretation of results. The mathematical formulation represents a model of production planning with the aim of minimizing production costs and meeting demand and resource constraints. Decision variables determine the selection of tasks and the number of resources assigned to each task in different periods. The target function minimizes the total cost of production, and constraints ensure that demand is met, resource capacity is not exceeded, and production times are respected. Algorithm implementing production planning problem based on the provided mathematical formulation. Using an optimization solver, such as QAOA or VQE, we can solve this mathematical model to obtain the optimal values for task selection and resource allocation variables, which will minimize the total production cost while satisfying the demand and resource constraints. The max cut problem is one of the most well-known optimization problems. It involves finding a cut in a chart so that the vertices are divided into two complementary subsets and the sum of the weights of the edges traversed by the cut is maximized. In the figure, on the left, a graph with 6 vertices and 11 edges of equal weight, and on the right, the solution to the max cut problem, where the vertices are divided into two groups, red and blue, so that the number of edges crossed by the cut is maximized, the black curve, which is 8. A more general formulation of the max cut problem is represented by QAOA problems. Hypothalamus artificial intelligence. Presence. OPTEX, optimization expert system. The optimization technology that allows you to assemble multi-problem mathematical models like a Lego game, using structured mathematical modeling. Can you imagine how? The optimization expert system makes it easy to making high-complexity large-scale mathematical models without programming. The foundations of OPTEX database algebraic languages consider the algebra as a standard, to express the relationships between the different parts that make up a mathematical problem. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Additionally, if two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming, MP, which in essence is a collection of algebraic elements. Then it is possible to join two MP problems to obtain a new MP problem. It is also possible to divide an MP problem into two MP problems. The multiple models are assembled like a Lego game, which can have as many groups of tiles as there are models. A mathematical model stored in an information system can be conceived as the union of mathematical components harmoniously integrated. There are two types of components, or objects. Basic mathematical definitions, indexes, sets, parameters, and equations or constraints. Advanced concepts, problems, models, decision support systems, and artificial hypothalamuses. These components can be stored in a relational information system. It permits their handling in a modular way. Following the principles of relational information systems, and use structured query language, SQL, to manipulate the mathematical objects. This conceptualization is independent of optimization technologies, which allows to separate the formulation of the mathematical models from their implementation, using a specific optimization technology. Do you wonder of how to make high-complexity large-scale artificial brains, without programming? The best way to make software is having to do it, is the goal of OPTEX. The high approach is aimed at developing cognitive robots that eliminate the tasks of computer programming, since the robot takes care of this process. This enhanced the mathematical modeling capacity of the professionals. The traditional process of mathematical modeling implies that programmers, usually mathematical modelers or data scientists, must make great efforts to implement complex optimization models. Starting from a real-world problem. For implementing complex mathematical models from MS Word, the stages are: first, convert the algebraic model to a formulation in MS Word, in the form of tables. Second, convert MS Word tables into CSV files in standardized ANSI format. This may require an intermediate step that goes through MS Excel tables. Third, upload the CSV files to the OPTEX database. This process is carried out with the support of OPTEX, which automatically validates that the mathematical elements are correctly formulated. Fourth, generation of the source program of the mathematical model on the selected computational platform. The second step may be shortened, loading the information from MS Word directly to OPTEX, using the MS Windows clipboard. The process of uploading OPTEX will be a more interactive activity through generative artificial intelligence, such as ChatGPT Omnichannel 4.0. In this way, the user will be able to communicate with the OPTEX model database, and use all the documents produced by HI for the management of the system. All through a conversation, out loud if you will, with OPTEX GPT. At the limit, if the user wishes, OPTEX GPT can perform the entire process in a single step, until the results are delivered. There is no need to store intermediate results. The basis of the OPTEX GPT conversation will be based on so-called prompting engineering, called by HI as the engineering of ideas. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus of the company is obtained. This is how the human brain faces reality. Multiple models of reality, acting permanently in parallel, to make decisions. The algorithm that simulates the hypothalamus is assembled by OPTEX, using the models that traditionally make up a decision support system. The concept of artificial hypothalamus can be applied to solve real-life problems from multiple points of view. In the diagram, the artificial hypothalamus coordinates models corresponding to the multiple problems faced by a company, organized from the point of view of its administrative functions. Another point of view is the spatial distribution of the problem. In this case, an artificial hypothalamus is presented for an agro-industrial company that has multiple facilities, farms, concentrated food factory, meat products factory, and stores in the food market. The entire relationship between the optimization models is stored in the expert system. Chaining OPTEX to super server in the cloud. In this case, the current one in the industrial environment, the programs are installed on a super server and solve the problem. The generation of quantum software in OPTEX involves accessing the expert system to generate the software into a computer code according to the quantum computer, like IBM Qiskit. Chaining OPTEX to quantum servers in the cloud. This is the new approach to the industrial environment in a short time. The structure of the OPTEX expert system supports the new functions required for the new interface. HI is working in this direction considering the studies carried out for the implementation of quantum AI. This involves the generation of new computational languages and their connection with quantum algorithms. OPTEX should be installed on any computer running MS-DOS where the programs to be sent to the quantum computer are generated. Chaining OPTEX to the quantum algorithm. HI's approach to quantum AI is based on two steps. The formulation of the models is based on OPTEX, optimization expert system, which generates the programs without the need to perform programmer activities. The algorithm already coded for execution is sent to the quantum computer. Chaining OPTEX to the quantum algorithm. HI's approach to quantum AI is based on two steps. The formulation of the models is based on OPTEX, optimization expert system, which generates the programs without the need to perform programmer activities. The algorithm already coded for execution is sent to the quantum computer. OPTEX generates the algorithm in an appropriate computer language, according to the availability on the quantum computer. OPTEX Optimization Mathematical Model Store. All models made by HI are stored using OPTEX, Optimization Expert System, producing a warehouse of proven mathematical models that provides a valuable resource for the creation of new models. OPTEX resembles object-oriented programming, where programmers reuse components that already work, which not only saves time, but increases the reliability of the developed models, which operate perfectly. In this way, OPTEX currently manages a warehouse of hundreds of models, created since 1978, and stored at OPTEX since 1990. OPTEX Optimization Mathematical Model Store prevents users of working models from having to perform a recoding process to have access to quantum computers. OPTEX opens a new path for thinking about mathematical modeling. Joint problems is much easier than writing equations. That's the future of mathematical modeling, which has been used for 35 years by OPTEX, the Optimization Expert System. Do not program, every programmer's dream. As George Bernard Shaw would say, imagination is the beginning of creation. You imagine what you desire, you will what you imagine, and at last you create what you will. Thank you very much for your attention.